All right, let's go on a quest for the absolute limit of temperature. We're talking about a journey into a cold so profound it actually starts to bend the very rules of reality. So, to kick things off, let me ask you a simple question. If you had to guess, where would you say is the coldest spot in the entire known universe? Just take a second. What's the first thing that pops into your head? Now, maybe you thought of Antarctica, right? It can hit a bone-chilling minus 120 degrees Fahrenheit. Or perhaps the dark side of the moon, a frigid minus 280. A really great guess would be the vast emptiness of deep space, which sits at a cool minus 455 Fahrenheit, just from the leftover glow of the Big Bang. But believe it or not, the coldest place in the universe isn't any of those. Turns out the coldest known spot in the universe is right here, practically in our own cosmic backyard. It's a man-made experiment about the size of a mini-fridge that is right now orbiting our planet on the International Space Station. Yeah, you heard that right. Humanity has created a cold that doesn't exist anywhere else in nature. So how is that even possible? Well, to get our heads around it, we first need to understand the core concept that makes this whole quest tick. The idea that there's an ultimate, absolute bottom to temperature. And that limit is called absolute zero. It's the point where particles have the absolute minimum energy the universe will allow. On the Kelvin scale, it's a nice clean zero. For the rest of us, that's a staggering minus 460 degrees Fahrenheit. At this temperature, all that jiggling and vibrating that we call heat, it basically just stops. Atoms become almost perfectly still. This idea of a floor for cold wasn't just pulled out of thin air. Scientists chased it for centuries. It started as just a whisper with Robert Boyle way back in 1665. Then Guillaume Amontons had a hunch that a gas's pressure must eventually hit some kind of zero point. And finally, in 1848, the famous Lord Kelvin connected all the dots, giving us the absolute temperature scale that defines this entire quest. Okay, so we have this ultimate goal, right? 0 Kelvin. But, and this is a big but, here's the cosmic catch. It is a destination we can never, ever actually reach. A fundamental law of the universe turns this whole thing into an infinite race to a finish line that we can get closer and closer to, but never actually cross. And it's all thanks to the third law of thermodynamics. Think of it like this. Cooling something is really just about removing its heat energy. At first, that's pretty easy, but the colder it gets, the harder and harder it is to pull out that last little bit of heat. It's basically Zeno's paradox. You can always get halfway closer to your goal, and then halfway closer again and again, forever. But you can never take that final last step to actually get there. It would literally take an infinite number of steps. But here's where things get really, really interesting. It's what happens when you get almost there. See, while we can't ever reach absolute zero, the journey to get incredibly close, well, that reveals something utterly bizarre, a completely new state of matter that totally defies our everyday intuition. As you cool down certain types of atoms, they're called bosons, they slow to a crawl. They get so slow that their normal classical identity just kind of fades away, and their hidden quantum nature completely takes over. You see, every particle also behaves like a wave, and as these atoms get colder and colder, their waves start to spread out, getting bigger and bigger until they start to overlap. And then, something that feels like magic happens. All those waves merge, and the individual identities of thousands, maybe even millions of atoms are completely lost. They stop acting like separate little particles and start behaving as one single massive quantum object, what scientists call a superatom. This is the fifth state of matter, a Bose-Einstein condensate. Now, this wasn't some lucky, accidental discovery. It was predicted way back in the 1920s by Satyendra Nath Bose and, the one and only Albert Einstein. But the idea was so extreme, so difficult to actually create, that it took over 70 years for technology to finally catch up. Then, in 1995, Eric Cornell and Carl Wieman finally did it. They created the first one in a lab, and that achievement earned them, along with Wolfgang Ketterle, the Nobel Prize in 2001. And that brings us right back to our little mini-fridge in space. The whole purpose of NASA's Cold Atom Laboratory is to create and study these Bose-Einstein condensates in a totally unique environment, pushing the boundaries of cold to create the undisputed coldest spot in the entire universe. So just how close have we gotten? Well, get ready for this. The current world record was set in a lab in Germany back in 2021, and it is a mind-boggling 38 picokelvin. No, not nanokelvin. That's billionths of a degree. This is picokelvin. That's 38 trillionths of a single degree above absolute zero. And the Cold Atom Lab in space? It's designed to get even colder. Okay, so why go to all this trouble? Why haul this thing into space? The answer, in one word, is gravity. On Earth, the second you create this super delicate cloud of atoms, gravity just yanks it straight down. The whole experiment is over in less than a second. But up in the microgravity of the space station, the atoms just float. This gives scientists what feels like an eternity, over a second, and they're aiming for way longer, to watch what happens. And all that extra time, it also lets the atoms expand and cool down even more, reaching temperatures that are just impossible to hit down here on Earth. All right, so now that we've seen the unbelievable cold we can create, let's take another look at the universe. How does our achievement actually compare to the coldest spots that nature itself has to offer? Well, the coldest natural spot in our solar system is right next door, hiding in a permanently shadowed lunar crater called Hermite. It gets down to about -415 Fahrenheit. But the coldest natural place we know of anywhere is the Boomerang Nebula, 5,000 light-years away. It clocks in at just 1 Kelvin, or -458 Fahrenheit. That's so cold, it's actually colder than the background radiation of deep space itself. So how in the world did it get so cold? Well, the story is incredibly violent. Scientists think a small star spiraled inwards and literally plunged into the core of its dying red giant partner. That collision set off a massive eruption, blasting the star's matter out into space at unbelievable speeds. And you know how a can of compressed air gets cold when you spray it? It's the same idea. That rapid expansion of gas acted like a giant cosmic refrigerator, supercooling the nebula to its record-breaking temperature. So let's put it all together. We can create temperatures that are literally trillions of times colder than the Boomerang Nebula. It's an incredible technical achievement, for sure. But why does it matter? What do we actually learn by pushing matter to these absolute extremes? This right here is the frontier of physics. By creating two of these super atoms from different elements and just watching them fall together, we can test gravity with a precision that is just mind-boggling. Einstein predicted they should fall identically, and any little deviation could point to brand new physics. It also lets us see these bizarre quantum effects, which are normally microscopic, play out on a scale we can actually observe. It's this incredible window into the fundamental rules of reality, and it could pave the way for things like ultra-precise quantum sensors and totally new kinds of matter. As Rob Thompson, NASA's mission scientist for the Cold Atom Lab, puts it, this isn't just about one single experiment. It's about laying the groundwork for a whole new field of science that happens in space. Every discovery we make just builds on the last one, pushing our understanding that much further. And so, we're left with this thought. We've learned how to chill atoms to a tiny fraction of a degree from absolute stillness. And in doing so, we've revealed a hidden quantum world. It really makes you wonder, what other fundamental secrets about the nature of our universe are just sitting there waiting for us to get cold enough to find them?